and welcome to 16.3. For 16.3, we're going to be talking about gradient vector fields. That's something that we saw back in 16.1, and we're going to look at connections between gradient vector fields and line integrals. So our learning goals for today are to be able to state and apply the fundamental theorem for gradient vector fields. We're also going to describe the geometric implications of the fundamental theorem of gradient vector fields. We're going to define what a conservative vector field is and its relationship to gradient vector fields. And then finally, we're going to develop a test to be able to quickly check whether or not a vector field that we have is one that is a gradient vector field or not. And we're going to do that by computing some partial derivatives. So the first question we're asking ourselves today is, why are gradient vector fields great? And to answer that question, I'm going to recall a couple of facts that we saw from the previous videos. So recall, we say that capital F of xy, this function, is a gradient vector field if there's some potential function, usually we write it with a phi of xy, such that the gradient of phi is equal to our gradient vector field F. That's where the name gradient comes from. Another fact that I want to recall is line integrals. So in the last video that we saw, we decided that a vector line integral over some path c of t of our gradient vector field f dot ds, we can compute this line integral regardless of what kind of vector field this f is. Our way of computing this is to look at where t goes from a to b of f evaluated at c of t dotted with c prime of t dt. So this was an equation that we learned last time, and this is summing up the amount of work that's done by this vector field along this path. And the cool thing, the thing that we're going to tie together today, is to consider this. Just for the sake of fun, let's take our phi function. Let's say that f is a gradient vector field. And let's look at our phi function, phi of xy. And let's plug in c of t into that function, the same path. And I want to look at what is the derivative of this phi function with respect to t. This sort of seems like it's coming out of nowhere, but you'll see where this comes together. So I'm taking my potential function, plugging in this path, and taking the derivative. And I need to use chain rule in order to be able to do this, right? So when I compute chain rule, I'm computing the derivative of the outside of this function. Sometimes we might write that as, well, I'll make my notation a little bit consistent. Phi prime of c of t times the derivative of the inside of the function. However, if we're evaluating this over vector valued functions, then when we talk about this derivative, the derivative of our phi function with respect to t, that's exactly equal to the partial derivative of the first component and the partial derivative of the second component. In other words, our derivative is our gradient evaluated at c of t. Dot product with, if I'm thinking of my path instead of a real valued function with outputs that are points, I'm thinking of it as being a vector valued functions with outputs that are vectors, then this becomes a dot product. And look what this leads us to. So the gradient of phi evaluated at c of t is exactly our f function. F of c of t dotted with c prime of t. So what did this just show us? This just showed us that I can think of this integral as being this interior chunk, by definition, is exactly equal to the derivative of my potential function, which means that I can rewrite this derivative to instead, I can rewrite this integral to instead be the integral as t goes from a to b of phi of c of t, looking at the derivative with respect to t. dt. So I'm taking the derivative of my potential function and then I'm integrating over t. And by fundamental theorem of calculus, this is where the magic comes. I'm taking the antiderivative of the derivative. What happens when I do this? By fundamental theorem of calculus part 2, this is exactly equal to phi of t evaluated at each of these endpoints, meaning that my grand conclusion is that this is going to be phi of c of b minus phi of c of a. This is something that you might recall from fundamental theorem of calculus. All of this work is summing up the facts that I will state are our fundamental theorem of line integral, of gradient vector fields. So this leads us to our fundamental theorem of gradient vector fields. If f is a gradient vector field and f has a potential function phi, then the vector line integral with some path c, which is equal to the integral from t equals a to b of the derivative of the potential function, is going to be exactly equal to that potential function evaluated at each of the endpoints of this time interval. So it's going to be equal to phi of c of b minus phi of c of a. You're asking yourself two things right now. The first thing you're asking is, what does this mean? And the second thing that you're asking yourself is, why do I care? So I'm going to answer those two questions in that order. In order to figure out what this means, we're going to do an example, and then to tell you why you care, we're going to look at the geometric implications. So let's start by looking at an example. So let's say that I have a vector function, and it's given by 3y minus 2x for the first component, and 3x in the second component. And let's say it has a potential function given by 3xy minus x squared. And I have some path over here, and my path in this case is called c of t, and it's equal to t in the x component and 5t in the y component as t goes from 0 to 2. So the first thing that we might want to do is to check and see whether or not is phi actually the potential function. This is sort of a review. What does it mean to be a potential function? It means that the gradient of phi has to be equal to f. So let's go ahead and compute. What is the gradient of phi? The gradient of phi in this case, looking at the partial derivative with respect to x, I'm treating y as a constant, and I end up with 3y minus 2x for the first component. And then for my second component function, I treat x as a constant, and I take my derivative with respect to y, and I end up with 3x. So notice that my gradient of my potential function is exactly equal to this vector function, f. And so I know that phi actually is a potential function. The next thing that we're asking ourselves is, I want to compute the line integral. And we're going to compute this line integral two ways to be able to compare our answers. So in this case, it's a vector line integral. And it's an integral as t goes from 0 to 2 of f of c of t dotted with c prime of t dt. This is our old-fashioned way of computing the line integral. And let's go ahead and walk through what it means to compute it the old-fashioned way. So from our chapter 16.2 experience, first we have to evaluate what is f of c of t. So I'm going to do a little bit of scratch work in blue and say, in this case, f of c of t, I'm going to take my c of t function and plug it into my f function. And in this case, our y values are equal to 5t and our x values are equal to t. So when I plug that in, I get 3 times 5t minus 2 times t for the first component. And then because my x value is equal to t, I'm plugging in t for x and I get 3 times t. And I can simplify this a little bit, and I see that my f of c of t function is going to be equal to 15t minus 2t. I can do that in my head. That ends up as 13t, 3t. So I'll go ahead and write that down above. That's the first step that we need to do. So I just found out what f of c of t is. My integral as t goes from 0 to 2 of f of c of t is 13t comma 3t. And now I'm going to take that and dot it with c prime. So I have to find out what my c prime is. Again, I'm going to do some scratch work down here in blue. And in this case, c prime of t, actually I don't think I need to do the scratch work. This is something we can do in our head. Thinking of c of t as a set of vector outputs rather than point outputs, I can write the derivative of the first component function is the derivative of t, which is just 1, and the derivative of 5t, which is just 5 dt. So now I make a dot product. Recall that a dot product, I multiply the first components and I multiply the second components and I add those two things together. So in this case, I end up with the integral as t goes from 0 to 2 of 13t times 1, which is just 13t, and then 3t times 5, which is 15t dt. I again can simplify this. 13 plus 15 is 28. So it's the integral as t goes from 0 to 2 of 28t dt. Now I'm in a position to be able to integrate. When I integrate this, I end up with t squared and half of 28, which is 14, evaluated from t equals 0 to 2. When I plug 2 in, I get 2 squared, which is 4, times 14, which is 28, and then 56 minus 0. And so I end up with 56 as my numerical answer. Let's keep that in mind. So this was all the steps that we needed to go through in order to calculate this line integral. Let's use our new magic trick, though. We have a new magic trick to be able to compute this line integral, right? We don't have to go through all these steps because we just found out that because f happens to be a gradient vector field, not all vector fields are gradient vector fields, so you can't do this with any old vector field. But in this case, because it's a gradient vector field, we're going to instead evaluate it at the potential function at the ending point and starting point. So this becomes phi of c of t minus, phi of c of 2, because that's my ending point, minus phi of c of 0, because that's my starting point. So let's do a little bit of scratch work to find this out. So let's first find out what is c of 2. I'm plugging in 2 for t for this function, and I see that I get 2 in the first component and 10 in the second component. While I'm at it, I'll go ahead and compute c of 0. And I get 0 in both components. It's sort of a boring one, but that's okay. And now let's evaluate phi at c of 2. So I'm plugging in 2 for the x component of phi and 10 for the y component. So maybe I'll write it over here. I see that phi of c of 2 is going to be 3 times the x value, which is 2, times the y value, which is 10, minus the x value squared, which in this case is 4 squared. No, it's 2 squared, which is 4. And phi of 0, it turns out, luckily, when I plug 0 in for x and y, I get out 0, so I don't even have to worry about that. And what is this? This is 3 times 2 times 10 is 60, minus 4, which is 56. Da-da-da-da. Hooray! The reason why hooray, we didn't even have to do any integration. I mean, we did have to plug in some values, and we had to do some numerical computation. But this, in general, is going to be a much faster and easier computation than having to go through the whole line integral process. So that's one reason why this is a really cool and helpful thing.